Okay, we're going to go ahead and talk about the more things change. The quote we have here is that God grant me the serenity to accept the things I cannot change, the courage to change the things I can, and the wisdom to know the difference. So we're going to talk about chemical and physical changes. Our learning goals for this lecture. Number one, describe the states of matter. We're going to go into solid, liquid, gas and just describe it a little bit. Describe the similarities and differences of elements. Here's some key vocabulary that we'll need to know: elements, compounds, homogeneous mixtures, and heterogeneous mixtures. Describe an object by its chemical, another good definition, chemical and physical properties, and distinguish between chemical and physical changes. What we should already know coming into this, that matter can exist as solid, liquid, and gas. There's some other states of matter, but we won't go into too much detail on those. Samples have different properties that can be used to separate them, and that matter can react with other types of matter. These are all things that we should know coming in from this from like 8th grade. What we kind of learned in the lab, that baking soda was a chalky white powder that does not react with the calcium chloride, and that calcium chloride was a fine white powder, sometimes in pellets, that does not react with calcium. The calcium, actually, the baking soda, so it doesn't react with the baking soda. And then we have acetic acid, that is vinegar, clear that forms bubble, reacts with the mixture of calcium chloride and baking soda. Other things, the reactants combine together to produce a new product. So when all of them are together, the acetic acid, the calcium chloride, and the baking soda, when they were all together, they produce something brand new, a new product. The bag also should have felt cold, and then the mass of the bag is the same before and after reaction. That is going back to something that is central in all science, is the law of conservation of mass. So mass can't be created or destroyed. Jumping on through, matter. Now, what matter is, we define it as solid, liquid, gas, plasma, fermionic condensate, and Bose-Einstein condensate. The majority of the ones we probably know are right here. These guys down here at the bottom, the fermionic condensate and the Bose-Einstein condensate, are a little bit outside of our class, but they do exist. But just looking at solid, liquid, gas, plasma, just looking at those things, it doesn't really tell the whole story. We have to get into a little bit deeper talking about other types of substances. So the first question we really ask ourselves, is it pure? And to distinguish if something is pure or not, we say that pure substances are composed of single elements, and we'll define these in just a little bit: elements or compounds. So it's made of a single one of these. So it's either one type of element or it's just one type of compound. It's just what makes a pure substance. Okay, pure substance are a homogeneous or homogeneous composition, meaning that they are the same throughout. Okay, they're identical in all parts of the sample and identical in chemical and physical property. And so that's what a pure substance is. Now, if it is pure, how many types of atoms are there? That's a question that we have. Well, if there is a single type of atom, we have an element, and there's a good vocabulary term for us. A single type of an atom, that means that we have an element. If there's multiple atoms, arranged in any different way, we have what we call a compound. Okay. Now, for it to be a pure substance, meaning it can only be just an element, or it can only be just a compound. If we have a compound mixed in with an element, then it's no longer a pure substance. To make it pure, it either has to be an element or it has to be a compound. It can't be both. Okay. Next question we have, if it's not pure. So what if we don't have it? It's not pure, it's not a single element, it's not a single compound, it's not pure, then is it uniformed? And what we say is that a homogeneous mixture or a solution is uniform composition of two or more substances, such as when we look at a milk, we can see that it's the same throughout. Milk is actually considered something else, but we'll kind of, for this example, basically what you can say is that you don't see anything floating in it. You shouldn't see anything floating in your milk. It's just kind of the same consistency throughout. The heterogeneous mixture is non-uniformed. Okay, it's non-uniform, and it's a combination of such a two or more things, substances like orange juice. So when we look at orange juice, we can look at this example here. We can see that here's the orange juice all up in here, and then you can see, hey, there's something floating in there. It's different than our milk substance here, that it's not the same throughout, but here we have something floating in it, and so that would be a heterogeneous mixture. And so this is how we break everything down kind of in a flow chart. Everything is made of matter. Okay, everything is made of matter. Everything that we can see, feel, touch, all that things, that is matter. The question that we ask ourselves in this flow chart: can the matter be separated into different things? If it cannot be separated, then we know that we have a pure substance. If it can be separated, so it has a bunch of different components to it, then we know that it's a mixture. Okay, we'll go towards the mixture side of this. If it's a mixture, is the mixture same throughout? If it's the same throughout, yes it is, then we know that we have a homogeneous mixture. If it is not, you can see things floating in it, then we have a heterogeneous mixture. Okay, so that if it can be separated, we know that it's a mixture, and then we just have to figure out what type of mixture we have. Okay. From here, we'll go to the other side. So if it cannot be separated out, we know that we have a pure substance. It's made of one thing. And then we ask ourselves, is there more than one type of atom present? If it's a single atom, we know that it is an element. If there's multiple atoms there, then we know that it's a compound. So that's kind of our flow chart of how we can distinguish matter. Now, some separation of mixture. So we remember the question that we had up here is, can matter be separated into different things? So if it can be separated, we know that's a mixture, and so we're going to go through a couple different separation techniques of mixture. The first one, which you should probably be familiar with, is filtration. Filtration is when the filter traps solid particles and the liquid part runs through the filter. Happens just like a Brita water filter, that the solid minerals inside that water, they're trapped in the filter, and the liquid H2O is allowed to drain out. Distillation. Distillation, this is how they get gasoline. We get that crude oil out of the ground, and they distill it into its different parts. So they take it, and it's where the liquid portion is evaporated off to leave the solid. We can either leave solid behind, or we can also separate different liquids that have been put together. And so we can boil it off at a very specific boiling point, and we'll capture just one specific liquid that way. Another separation technique, decanting. Decanting we'll actually do in the lab. It's where you take a beaker, and it's when liquid is poured off after the solid is settled to the bottom. Centrifuges, here's a picture of a centrifuge right over there, and it's a machine that spins a sample very quickly so that the components with different densities separate out. And then we also have paper chromatography. We can do this with ink. It's used to separate mixtures because different parts of the mixture bind to the paper and move slower than others. So if you put ink, ink is made of different colors, black ink especially, and if you put basically a liquid that moves up through the paper, as it moves, each particle will separate out because some move slower than others, some are bigger than others. So jumping into our first example, it says classify the following substances as element, compound, homogeneous mixture, or heterogeneous mixture. So when we're looking at this, and we can see this as kind of a picture of a mock-up of some compounds. We know that we're looking at these. Here's a compound right here. We can say that the red and the blue are different atoms put together. And then we could say that this right here is a molecule since it's the same atom put together. But when we're looking at it, what we would say is that this is going to be a heterogeneous mixture. The reason why we can see it, there's different parts to it. We can see that this is kind of settled, the red and the blue bonded together. They're kind of settled at the bottom, and these guys are settled at the top. And so we would be able to see a difference between those two things. So we call that a heterogeneous mixture. Moving on here to our next example, it says classify the following substance as an element, compound, homogeneous mixture, or heterogeneous mixture. And so when we're looking at this, we can see that this is going to be brass. It's a brass instrument, and so it's a homogeneous mixture. The instrument is made of brass, and brass is uniform throughout and is made of various elements. The correct name for this would be alloy. We would call this an alloy because it's a mixture of metals, but basically it is a mixture, and since we can't see little parts floating around in the other metals, they're all kind of one thing, we call that the alloy, that we would call that a homogeneous mixture. And our last example, it says human blood is a heterogeneous mixture, and it says plasmapheresis is the process by which blood is removed from the body, separated into its cells and plasma. The plasma is then returned to the body. Determine the most effective method for separating blood cells from the plasma. Justify your answer using the clear method. So when we're looking at this, we look at our conclusion, our evidence, and our reasoning. So when we're looking at this, what we would say here, since this is plasmapheresis, since all the different particles of blood have their different sizes and everything, what we would do is a filtration using a centrifuge to speed the process. So we would use a centrifuge to separate it out. That would be our conclusion. Our evidence: blood cells are much larger than water. And then lastly, our reasoning: a filter will trap the large cell while the smaller water will pass through. A centrifuge will provide greater force, speeding up the process. And we couldn't use anything like distillation because that would destroy the cell, or paper chromatography would render the cells useless as well. So we would have to use our centrifuge with a filter. Moving on, physical properties. So physical properties, that is a description of an object that is not related to its ability to change to another substance. In question we have there, is density a physical property? When we're looking at these physical properties, it's not related to its ability to change to another substance. So it's a property on how it is, not how it's going to react with something else. So yes, density would be a physical property. When we're looking at this, we see that we have a list of physical properties. These would be mass, color, temperature, absorption, malleability, area, pressure, specific heat, viscosity, density, boiling point, freezing point, brittleness, magnetism, volume, solubility, thermal conductivity, and ductility. So all of these would be a list of physical properties that we have. The main thing is that it's not how it reacts with something else, it's just how it is. It's a characteristics of how it is. So when we're looking at the lab, did any of the following have changed the composition of the fluid in the bag? Mixing the calcium chloride with the baking soda, and we didn't mix it with phenol red, but we mixed it with our baking soda. What changed it? Well, it's when they all mixed together, it created something new. When we're describing those things, that would be a chemical property. That's a description of what will happen when or how an object can change into something else. So when we're looking at this, it's basically chemical properties are how it reacts with other things, other substances. So a list of chemical properties would be combustibility, emitting of light, reactivity, ability to change color, corrosiveness, ability to decompose, explosiveness, and the ability to give off heat. That would be some examples of chemical properties. So let's jump into an example. It says, describe the physical and chemical properties of the sun. Some of the physical properties: that they have high temperature, yellow gas, and some of the chemical properties would be that the sun consists of hydrogen that reacts readily with many other substances. So saying that it had a high temperature, saying that the color of the gas was yellow, those would be our physical properties, and some chemical properties would how that hydrogen in the sun reacts with other elements. Moving on to our next example, it says scientists discovered that a potassium dope Buckminster Fuller molecule becomes superconducting at 18 degrees Celsius. Describe the chemical and physical properties in this narrative. We would look at this and say that, well, it's at 18 degrees Celsius, so that would be a physical property that it's very cold. That when we're looking at this, we would also say that since it's that cold, we would say that it's solid, and we would say that it's superconducting. That would be another physical property of it. A chemical property of it, since it's superconducting, we would say that in this substance it doesn't react with anything else. It stays by itself, and since it's unreactive, that would be a chemical property. Moving on to the last one, it says archaeologists uncover what they believe to be an original copy of the Magna Carta from 1215. What type of properties should be examined given the unique artifact? So when we're looking at this, what we want to do is we want to look at physical properties, because when we look at physical properties, we're not going to damage it. If we look at the chemical properties, that will result in the destruction of the sample as it's converted into something else. So we don't want to see how this article or this artifact reacts with other things, because that would just destroy it and break it. So we want to look at the physical properties of it. So in looking at that lab, when we mix the powders, nothing really happened. They didn't do anything. And what happened when the acetic acid was added? Well, then we saw a chemical reaction happen. So when we're looking at this, we had two types of changes. We had when the two solids were mixed together, nothing really happened. We physically mixed them together. And so a physical change is something that changes the form but not the identity of the substance. So good definition here. Physical change is something that changes the form but not the identity of the substance. So an example of this is a water is placed in the freezer. It's still water, just it turned into solid form. So this is an example of H2O. This is an example of H2O when it's solid. Nothing really changed, it just changed its form, so we would call that a physical property. Evidence for a physical change, change in shape, change in state, change in temperature. So we can go from hot to cold, but we'd have to get that temperature change from outside the system, not within the system. And a change in texture. Those would be evidence for a physical change. Now, a chemical change, on the other hand, is the process by which a substance is changed into a new substance. So when we added the acetic acid to the baking soda and the calcium chloride, it changed into something brand new. We put a cup of water with electrical current running through it. It's called electrolysis, or the splitting of water into hydrogen and oxygen. So we take this water molecule, we add electricity to it, and it breaks up into an oxygen our hydrogen and our oxygen atoms. And so that's breaking apart into something different. Water is a liquid at room temperature. If we were to break water apart into hydrogen and into oxygen, the hydrogen and oxygen would be gas at room temperature. So it changed into something brand new. So evidence for a chemical change, it's producing of gas bubbles, and the main thing here is producing gas bubbles. When you open up a Coke, you see the carbonation come out of it. That's not producing gas bubbles. Those bubbles were dissolved in it. But if production of gas occurs, then we know that that's a chemical change. Change in temperature. So if this is a different kind of change in temperature, if we put water into a freezer, yes, that water changes temperature, but not because it's reacting with something else, just because it's in the freezer. This change in temperature would occur from the chemical change itself. Substances disappear, so it turns into a gas. A precipitate forms. This is when you put two liquids together and you see some stuff starting to float in it. That would be a precipitate. A color change, odor produced, and apparent change in mass. And so we would say, well, it became more massive. We didn't create the mass, but the mass might have come from the air. So oxygen could attach to it, and the oxygen from the air would combine with something else to basically give us a little more mass. We didn't create anything, but we still have more mass in our beaker or whatever we're measuring. So let's look at an example. Name one example of a physical change and a chemical change done in the kitchen when preparing a meal. Physical change could be blending, chopping, crushing, melting, freezing, or mixing. Those are all physical changes. Some chemical changes, those would probably be cooking. You can think of cooking, baking. So when you bake a cake, searing, and those types of things would be chemical change. It changes into something new. And then our last example. It says that you mix yellow Kool-Aid with red Kool-Aid and notice a distinct color change. Determine whether a physical or chemical change occurred and justify our answer using that clear method, conclusion, evidence, reasoning. So when we're looking at this, we would say that this would be evidence for a chemical change. Mixing two different Kool-Aids does not result in a different substance. When we're looking at this, we're looking and see, yes, we do have a color change here. So it might be evidence for a chemical change, but remember, when we're putting those two things together, it's just because those two colors mixed. We didn't create color. It didn't come from somewhere. So we took that red, we took that yellow. So the first thing we might think, say, hey, color change is a chemical change. Well, not all the time. We have to make sure that how it changed. We got two separate colors. We got yellow and we got red, and we mix them together to get a different color. Not necessarily a chemical change there. So we got to look at the details anytime we want to look at chemical or physical changes.